Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is another lecture in the Exponential Functions series, and it's meant for college algebra students who have been pre-exposed already to exponential functions and all the properties of exponential functions. And now we're going to dip our toes into one of the most important bases in exponential functions, which is base E, the natural base. So I like to derive this a little bit using calculus. So we're going to play with calculus today. So if we're considering that we're only going to invest $1 and only for 1 year, the amount we have at the end of the year is the following. Now remember, this is from the previous lecture where we had the compound interest formula. This would normally be how much we invest, and we'd normally have a t on the end of that because that would be how many years we allow that investment to run. But in this case, I'm saying, nah, we're only going to let t be 1, run it for a year, and we're not rich, we only got $1. So that's how we're doing this problem. But we're going to make a really wacky, non-realistic assumption. We're going to assume that our rate is 100%. That is, R in that formula is just going to be a 1. And then if we do that, our expression simplifies completely down to this beautiful 1 plus 1 over n raised to the n. Again, this comes from the compound interest formula, which is this guy right here. Just we basically assume that that's 1, and that's 1. Otherwise, it is the compound interest formula. Once we've made that assumption, we can really start playing with this. Let's go ahead and approximate the horizontal asymptote for that function by building a table of values. And to do this, we're going to use Desmos because I don't want to sit here all day and do this. Notice that I've changed the arguments from n to x's. That's just traditional, because n's are typically natural numbers, 1, 2, 3, 4, and functions are not discrete. They are continuous. They go over the continuous real number system. So you can plug in any value between, let's say, 1 and 2. You should be able to at least. And so because of that, we don't want to just use n's. That's why we choose x's. But we want to look at the horizontal asymptote for this function. And recall, horizontal asymptotes are the behaviors of the function as x runs off to positive or negative infinity. That already starts the calculus right there. So let's go ahead and run over to Desmos as quickly as possible. And here, all I did was just type in the function 1 plus 1 over x raised to the x power. And we're going to build a table so that we can investigate what these values are as x goes to infinity. Notice when you plug a table into Desmos like I just did, it gives you a header up here, x sub 1 and y sub 1. I don't want y sub 1. I want that to be f evaluated at x sub 1. It's just a lot cleaner because it's going to use the function that I typed. So x is going off to positive infinity. Well, then typing in 1 is silly. Typing in 10 is silly. Typing in 100, silly. Typing in 1,000, silly. Typing in 10,000. Well, how about 100,000? Well, how about, 100,000 or a million? You keep doing this. By the way, you should notice that our y values are somehow, in some way, magically centering around a number. So if I put a 1 with 1, 2, 3, 4, 5, 6, 7 zeros behind it, or a 1 with 1, 2, 3, 4, 5, 6, 7, 8 zeros behind it, 1 with 3, 4, 5, 6, 7, 8, 9 zeros behind it, you can see it's really honing in on 2.71828. And so this seems to be fairly convincing that this must be approaching something magical. And it is. This is called a limit of a function. As x goes to infinity, it looks as though our function is approaching 2.7182821. And that, by the way, is actually a flaw in Desmos that is not actually fairly accurate. And if you put more zeros into that, you'll find that it's actually wrong. It starts to approach 1, which is not true. But if you use a good computer and a good calculator, you'll find that f of x actually approaches 2.7182828459045 and so on and so forth down the line. Those are the numbers those are the digits that I have memorized for this, but that's what it's approaching. That is a very, very special number, and that's why I've memorized it. You see, that number is what we define to be E. E is approximately 2.7182828459045233536 and so on and so forth down the line. That is the limit as x runs off to infinity of 1 plus 1 over x to the x power. It is known as the natural base, and it is super powerful for us. The natural base leads directly to the natural exponential function e to the x. I'll highlight that there. Which represents continuous compounding. This represents what would happen if instead of having something, like some investment go 12 times a year, we might want to have that investment go daily, 365 times a year, get interest, right? But then somebody comes in the room and they say, no, I don't want 365 times a year. I want it to happen every hour. Well, there's 24 hours in each of those days, so I'll do this. Somebody else says, no, I want it every minute. Well, there's 60 minutes in every hour, so I'll do this. Notice these numbers are getting larger and larger. Eventually, you're tending to huge numbers or to infinity. So this is basically saying, what if you were to compound not just every day, not just every hour, not just every minute, not just every second, not just every nanosecond, but every single slice of time that you compound. So you take whatever your rate is, you divide it by the number of slices, which are an infinite number, don't get me wrong, and you collect interest on those infinitesimally small slices. And that is called continuous compounding. This is the type of compounding that nature takes on. For example, a flower does not suddenly increase in height by 12% every week. Instead, it's continuously growing. Continuously compounding used to, back in I think it was the 80s, it was allowable by banks and credit cards to do continuous compounding on debt, which gave them the most money. Because remember, the more you compound, the more money you get. So continuous compounding maximizes the amount of money you can get if somebody owes you money. So until it was made illegal, banks were doing continuous compounding. Now, rather than break this video into smaller chunks, this one's fast enough I can do all the continuous compounding stuff in one conversation. So let's investigate continuous growth. For all real numbers t and all positive numbers p naught, continuous growth or decay is represented by that famous formula that all algebra students know, PERT. P of t is equal to p naught e to the rt. So the initial value is p naught. R is considered to be a growth rate if R is positive. I'll highlight that, continuous growth if R is positive. Otherwise, it's a continuous decay rate if R is negative. And that's the growth or decay rate per unit time, and T is the elapsed time. So this is kind of the background for exponential growth in the sciences. So let's go ahead and use it. They're actually pretty easy to use. A person invests $100,000 at a nominal 12% interest rate per year, compounded continuously. Well, right there, I have pretty much everything I need. I know the initial investment was $100,000. E to the rate was 12%, so 0.12 t. That's it. These are a lot cleaner to write than the non-continuous compounding or the discrete compounding case. Great. What will the value of the investment be in 30 years? Well, that's kind of easy. Just P of 30 is equal to 100,000 e to the 0.12 times 30. And then we go over and grab a calculator, right? Let's go ahead and do that. What's nice about this is in Desmos, if you're in the scientific calculator, you could define a function there. You could say my function's 100,000. It's 100,000, right? Yep. E raised to the 0.12 t. That's your defined function. And you could say, what's that value after 30 years? And it'll tell you. That's actually pretty good. It's $3.6 million. Now, remember, you invested 100,000. And after 30 years, you have $3.659 million. Now let's change the name of the game a little bit. Let's say that we had that same investment, but I'll call it Q this time. And so we still had the 100,000 to invest. Okay, there we go. And we're going to invest it at a discrete rate of 12% still, but we're going to only compound that once a month. Now remember how the formula goes. Just in a 12 here and a T. And now we're going to see how much that investment is worth after 30 years. If you compare those two investments, one is $3,659,000. The other one is $3,594,000. The difference of which is P of 30 minus Q of 30 is a $64,859.31 difference. So continuous compounding earned another $64,859.31. And this is why, back in the 80s, it made sense for credit card companies to do continuous compounding. It's not that somebody would have $1 million or $100,000 in debt. It's just that as a group of citizens, as a country, they would have millions of dollars in debt. And that continuous compounding would give them great advantages in interest. So that's why it became banned at some point once the mathematicians kind of started shouting about it and saying this is not right because the world does not work continuously like that. Only nature does. So there you have it. That's how much we'd have at the end of 30 years. That's a pretty good example. And the final example is very famous. Whenever you have radioactive decay, it presents famous examples. So radon-222 decays at a continuous rate of 17.3% per day. That means that you have e to the negative 0.173 t. Let's see, how much will 100 milligrams of that, so here's our initial amount, 100, how much of that will remain after 3 days? Right? How much of that will decay, that's hard for me to read. How much will 100 milligrams of radium-222 decay to in 3 days? And how much will remain after 1 year? Okay, so I want to know what's P of 3. It's the population of that after 3 days. And then P of 365. What's the population at 365? Now, these require calculators. There's just no way around it. And my students often ask, well, then you're going to allow us to have a calculator on the exam, right? Because, well, I normally don't. I don't like to allow calculators on the exam because it can lead to lazy mathematics. Knowing that you have a calculator near to you, you start to think less with your quantitative brain and more with your Google brain, where you want something to answer something for you. But yes, it is true that to perform these computations, you do have to have a calculator in hand. I can actually write problems that are like this where you don't get to use your calculator, but it's no fun. I like you to see things going on. So, all right, what is the population of the Radon 222 after 3 days? Well, there's only 59 milligrams of that sample left. I'm just going to write that on my piece of paper. I'll round that, by the way, to the nearest decimal place. So 59.5 milligrams. And after 365 days, so P of 365, well, look at that. Hardly any left, right? This is 3.8 times 10 to the negative 26th power. That's essentially zero for the most part. Very, very small number. So it's all depleted at that time. So now that we've reached the end of this stuff, I'm trying to think of like, what are the little tips and tricks I can give you? Most of it you've seen in your prerequisite courses. The one warning I would have is that anything to deal with exponentials and logarithms in a college algebra course or beyond, it's going to be all applications. So you're going to see a lot of radioactive decays. You're going to see a lot of half-life problems and double time problems, that type of thing. And that's what I think makes it fun, to be very honest with you. I really enjoy exponential functions, and I really think that they model, especially logarithmic functions, model human behavior, and it's done so beautifully. So, anyhow, we'll get to that in a little bit.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.